So today's session is on how we can use advanced computer modeling to study extreme weather events. I'm joined today by Dr. Yunqing Xuan. Thank you, Yunqing, for joining us.
Thank you, Adam, for inviting me to give a talk. It's quite interesting, first time for me.
Great. Dr. Xuan is a graduate of Swansea University in Nanjing and has been working as an associate professor at Swansea University for almost 10 years, based within the civil engineering portfolio. He's worked and practiced as a civil engineer and a hydro-meteorologist in China as well as elsewhere, and leads a lot of top-class research that we're going to hear a bit about today. So Yunqing, I'll hand over to you.
Thanks, Adam. Now I'm going to be sharing my screen. Good morning, everyone. Thanks for joining us today. So I imagine I'll be giving a kind of taster talk about the things I've been doing and how you're going to expect. So in terms of teaching at Swansea, using this sort of online platform, let me start with my PowerPoint. Yes. Can I double check everyone can see this?
That's good, Yunqing, yes.
Okay, now I'm starting. So my talk will be lasting around 40 minutes also. During my talk, please do feel free. If you have any questions, please drop a message in that Q&A session, that chat box, so I can pick it up if possible, so answer your question directly, or wait until I finish, and then you can have all sorts of questions. Myself, as Adam already introduced, I'm an associate professor working in the civil engineering portfolio. Now we have a faculty of science and engineering. Originally, we were part of the College of Engineering. So I graduated from Swansea University, as Adam mentioned, quite many years ago, I would say. I will show you some of the interesting impact on my career from my background from Swansea, as well as my work, past work in Beijing, in this topic. Okay. Well, let me start. So the topic today is about advanced computer modeling for studying these extreme hydroclimatic events. Well, I'm based in a civil engineering sort of portfolio, but my research line is in the Think Center for Computational Engineering. So this sort of outline on my talk today, I will start with why I do this at the beginning and my personal motivation. And then I will touch the kind of topic about why do we have to use the computer modeling for flood forecasting and how do we do that. And then I will talk about two main aspects. So say one is we have a radar-based, so the precipitation forecast or estimation, and the other one is a big computer model called Numerical Weather Prediction, together with hydrological modeling for flood forecasting. And then finally, I will be presenting kind of very interesting recent study in Guangzhou, China, regarding this kind of extreme event, highway flood. Just happened, I think, last year also, to see how our work has made great contribution to the local development there as well. And then if there are any questions, please do feel free to ask. Well, talk about my work many years ago in China. Actually, this was my first job. This was the working place, so to say. I got my first job in the Ministry of Water Resources back in 1990s. In Beijing, you can see the title there, is the Hydrological Forecast Center. So I worked there as a civil engineer responsible for Asian flood forecasting for several big rivers in China, include Changjiang, which is Yangtze River in the middle, as well as the Pearl River in southern China, in Guangzhou, near Hong Kong, if you want to know the place. And then, of course, this wasn't wasn't the real working place I was there. I took this photograph, I think, 5 years ago when I visited Beijing see some of my old friends there. You got a sense more or less about how this flood warning, flood cycle forecasting, how important they are. You see that Porsche office with all the monitors, big screen. It wasn't a flood season, however, still there's somebody working there 24 hours a day with different shifts, of course. So my personal motivation at that time was because I had to deal with this big river, this Yangtze River. I grabbed this image from internet. Somehow you can get an idea. If you're from China, you know exactly what I'm talking about. So this is a big Yangtze River catchment. So it originates from Tibetan Plateau and all the way down from Sichuan and Hubei, and then Jiangxi and other provinces, and we are then finally reached to this outlet actuary area in Shanghai. It's more than 5,000 kilometers long, and this whole area, and you can imagine, it's huge. It's around 1 million square kilometers. It's much bigger than many countries in the world, so to say. The problem was, normally there's a flood season starting from early summer, and initially from upstream, you get the coming water along the river here until reach Chongqing, and there are several big sort of contributors, branches from the north as well as from the south. So they join together at this city, also quite, I would say, quite big city, is Chongqing. And then the flood water will be propagating down the stream to Yichang. This is where the Three Gorge Dam located. You see Three Gorge Dam here. At that time, when I worked in the office in Beijing, the dam had not been built yet. So the problem is this big amount of water coming all the way down from Chongqing and down to Wuhan. The traveling time is around 12 days or sometimes 2 weeks. And for Wuhan itself, of course, Wuhan, is famous for the virus, it's called the COVID, it's starting here. But at that time, always every year, you have this big problem. The flooding issues, not only the water from upstream, but also another one from Hanjiang. So my job is to predict what's going to be happening in 12 days. As you can imagine, during the 12 days, we could have more and more precipitation or rainfall falling down in between. If we don't know how much or the internal amount of precipitation falling down, we wouldn't be able to make any accurate or sensible forecast at all. So that was a big problem. So that is why I started my career as so-called hydro-meteorologist, to combine use computer modeling with hydrology and meteorology. Right. To follow this up, so the main idea for me, I think, well, we should combine these two techniques, two modeling systems. One is how we can make an accurate forecast of rainfall or precipitation, and then how we can use that precipitation forecast into the hydrological forecast, or in a way to forecast flooding in any area. So the main challenge, of course, is accuracy. So accurate precipitation forecast is needed for large river basin like Yangtze River. But interestingly, we cannot always have accurate, or at least as accurate as we expect. This sort of forecast not available. And at that time, I still was a practical case, so to say. Many people, engineer, what they do, they make a sort of what if analysis. So if there's kind of 20 millimeter precipitation or rainfall falling down on the ground, and then what's going to be happening? So this sort of what if analysis, it's useful to some extent, but as you can imagine, not accurate. So what we really need is so-called quantitative forecast. We need to know the quantity, the timing, the location, and this is a name called quantitative precipitation forecast, QPF. On the other hand, if you look at a small area, this is another extreme case, of course. This is happening in 2004 when I was doing my study here in the UK, in Bristol. There was a quite special case called Boscastle, extreme flooding. It's a very small village near the coast in Cornwall, very beautiful place. But on that particular day, 16th of August 2004, the heavy rainfall happened just half an hour. Within half an hour, you see this thing happens. So several people just sitting in a coffee shop and watching around, and suddenly found their car floating around. There's no way people got warning beforehand because it happened so quickly. So when the so-called rainfall stopped, you see the consequence already. So this is so-called flash flood, all the way flash down the valley. So that is a problem. They also showed or highlights the need of having this QPF in place. For example, if we had such precipitation forecast, several hours beforehand, we wouldn't have such a problem. Okay. This is, you see here, we have such a need for big catchment. Also, we need to have the sort of this QPF in place for the urban area, for small area as well. So that is a motivation. Before I can talk about this forecast, so let me talk about how we get this sort of information in the first place, or observation. Normally, this are the rainfall information we can get is from Raingauge measurement, the first to the left column. And then nowadays we have the remote sensing. We have radar, but this is radar for not for detecting airplane, it's for detecting rain droplets. So the rainfall radar. So these two sort of information source we can have. Raingauge is direct measurement, radar is indirect one. I'm not going into detail about this comparison, but I will show you how they measure this sort of the rainfall amount. This is how a Raingauge looks like. What you see here to the left-hand side, you see this, we have a big funnel on top and collecting rainwater, and then drop down here, there's a magnet here, which can tipping. I will show you the animation, you get an idea. So as the rainwater coming down, so see this bucket can tip from one side to the other, and again, depending on how much water it collects, it can have how many different, tips, number of tips. It can get a record of tips, it can get a Raingauge measurement. Right, let me move to the next one. On the other hand, for radar, it's quite different story. Weather radar was actually invented in 1940 in the Second World War. It's a byproduct of this kind of aeroplane radar. Initially, people observed the sort of background noise when they try to monitor aeroplane, and they see this background noise. Then they realize it background noise actually is reflected back of magnetic wave from raindrops. So they came up with the idea, why don't we just make use of this noise to calculate how much rainfall there? That was how the weather radar was originally designed for. And to the right-hand side, you see nowadays we use this weather radar to observe, to monitor this rainstorm. This is a real rainstorm happened on the, you can see the date here, 2006 is 7th of December. The winter storm here, the big storm moving in. And nowadays, weather radar has been widely applied in many different countries. Of course, you probably see this from time to time on the TV screen, weather forecast, weatherman, weather lady, they show you the picture. So the fundamental idea behind this is use this so-called radar equation. Of course, I cannot cover that bit in detail, but just to give the idea, just measure how many raindrops in the cloud and reflected back as an energy, electromagnetic energy, as so-called reflectivity, and link this to the rainfall rate. So immediately you can sense, well, the advantage of using this sort of measurement is it can give you a quick scan for a very large area compared with rain gauges. So this is why in any country nowadays, you may see this. This is an example in the UK. In the UK, we have more or less it's old data, around 18 weather radars in operation. It was in 2010, but now I think one more they invested into this network. So with this sort of network, we can get a whole coverage of entire UK. And not only that, we can provide this kind of 5 kilometer resolution and 15 minutes every 15 minutes. So you got to scan every 15 minutes for the whole of the UK. And in some other cases, if we want to increase this kind of frequency, we can have 1 kilometer resolution and 5 minutes. So this is probably the best ever we can get in terms of rainfall or precipitation observation, which is quite handy. This just shows the idea how radar observation look like. This kind of grid-based, you see the distribution over small river catchment here. On the other hand, you have the rain gauge measurement. It's after interpolation. It's not very good compared with radar because we have many radar grids here. Of course, they have some certain disadvantages as well. Once again, I cannot cover that in great detail, but just for information, generally speaking, there are noise within. So this is why, so our research group here in Swansea, we develop all sorts of algorithm, the computer modeling, trying to correct bad, so improve the quality of the radar QPE. This is actually a big project we run, I think 5 or 6 years ago. It's a UK-wide project. So they're looking at a new radar in Thurnen to the south of London. London somewhere here. You see the actual London here and the Thurnen radar here. This is a new type of radar with dual polarization. Once again, I cannot cover that detail, but just for your information, but this radar can tell the type of precipitation, whether you have raindrops or you have snowflakes or your hailstone. So that's kind of quite an advantage compared with the traditional radar. And in Swansea, I took this photograph. Actually, I have the two radars, got a vertical pointing radar. This is on our delivery yard. You see here, this Swansea University. We can detect this kind of noise vertically. Therefore, this will help us to remove this kind of strange echo. This is called a melting layer. So this very fundamental called a research facility we are having. And also it's quite unique. I believe we are the only group in the UK or even Europe to have this sort of weather radar. The other example, I think it is in North America, probably in United States. And after we have this sort of radar observation, of course, we cannot just stop there. We try to make use of this radar information and to run our hydrological model, to run flood forecasting. And we published this paper, some years ago. Basically, we try to check the quality of the weather radar to see whether it is useful in such a scenario where we can couple the weather radar data with several other hydrological models. This is from Danish Hydrological Institute, DHI, Max Shi. The PDN model is another model from the UK CH. We have a lump model. We have rain gauge measurement as well. We have this combination, so to say. So you see this is our studies catchment. The main purpose is to make use of this new radar information compared with traditional approach to see how it can be useful in the context of running flood forecasting. And apart from that, we also been doing this sort of research, trying to combine the weather radar information with the gauge-based measurement as well. So you see that you have a radar grid here, and then you have this gauge measurement. So how we can combine them together, that is a hot topic in hydrometeorology as well. And our group has been doing this similar the research in this area as well, just show that some sort of idea. This is called the Kriging Interpolation-based merging. Basically, you trying to quantify the spatial relationship between the Raingauge data and trying to impose that sort of relationship to the radar measurement as well. And in the end, you combine them together, you take advantage of both sources of data. So that is the idea. And then another case study it happened, I think the event happened in 2015, so-called Christmas flooding in northern England, in Carlisle, seen in Carlisle, and a very beautiful place, but also famous for the flooding. And we use this sort of tactic trying to improve the quality of weather radar. And then we also run our model to check against the kind of observation, and we saw a big improvement as well. Well, so far I've been talking about the observation. Observation means you see just what already happened, right? What about if we want to know something in future? That means we want to have a forecast. So we also have facility for doing forecasts. Well, there are two ways. One is so-called based upon computer model. The other, again, the computer model, but based upon radar data. So we run this huge weather model, so-called numerical weather prediction. What you see here, we look at a small area, but firstly, we need to get a model run for the whole, so the entire world, for the whole Earth surface, and then we look at a small area, and again, we zoom in. If you think about this process like a zoom in process, looking at the dynamic happening at different scale, and finally, we can reach it to a very, very small area with very, very high resolution. This is how we do the modeling work. And vertically, you can split this atmosphere into different layers. It also increases the resolution, for example, a few hundred meters. But down to the ground, it is just a numerical solution of several physical equations. You can see here, if you had an idea about the kind of fluid dynamics, there's something similar here. We have so-called momentum equation, the first three, and we have continuity equation, the divergence of that flow equal to 0, conservation of mass. And we have an energy equation. So in the end, it's just how we solve this equation onto the global grid, and then the local grid, and then the regional grid. Right, it's very complex, of course. We cannot cover that a bit, but just for information, for doing this, we need to have supercomputers. And we actually have done that. This is for the Boscastle study. And you can imagine that down to the right corner, you see this weather forecast from the course model, from global model. Global model gives you a good idea about generally what can happen in your area, but it cannot tell you too much detail. So this is why we have to zoom in and we have to run another model. And you can compare with this, what really happened is Boscastle and the forecast. In the forecast, you don't see that at all. This is why we have to run a small model in our lab. It produces kind of so-called ensemble, different realization of this forecast. We see here, they are all different. Here and there, this is why it is necessary to run models several times or to run several models all together. This is so-called ensemble to account for the uncertainty. And on the other hand, this kind of high resolution model give you a whole idea about what's going to be happening. You see this strong rainfall. If you increase the resolution, you get a good deal about this kind of precipitation forecast. Initially, you only can reach around 30 millimeter per hour. It is not enough to drive flood. So this is why we have to use high resolution model. This is about numerical weather prediction. And then we run this is an ensemble flood forecasting as well. It's a very good example, coupled with small catchment, and then we have this ensemble forecast. Not only we have long period so-called capacity in time to make a forecast, but also we can account for the uncertainty as well. And more recently, I think 3 years ago, we collaborated with UK Met Office, which kind of meteorological authority in the UK, to couple their so-called the world leading model with our catchment model. And we have a huge computer resources, so to say, HPC, supercomputer here to support this kind of activity. And we made a great achievement. Now we have set up this whole model chain on our HPC, supercomputing wheel, to run whatever they can forecast within 2 weeks' time. So this is the latest development. And this is the sort of result of that kind of project we had with the Met Office, with the Welsh government. So the second source of this kind of rainfall forecast is from the weather radar itself. If you can think about the weather radar, you saw that animation of rainfall system, moving around. You can actually so-called extrapolating that image movement and make a very good forecast as well. That forecast, because it is very short forecast, we call it nowcast. The idea is you look at the radar echo or radar image, one after another every 5 minutes, you can get a sort of idea about how it can move in different ways. And then you do the extrapolation. That is called radar nowcast. But of course, in reality, it's not as simple as that. Just give you a nutshell about how it is done. So called radar nowcast. This just shows you how it's done. You get several radar images. You see they are very similar and moving around. And they can extrapolate, and you can get an idea about how the rainfall system will look like in 30 minutes also, or in 1 hour. So this is a very short range forecast we call nowcast. And our research, not only we want to combine this NWP and the radar, because NWP can look much, much longer into future, not just 30 minutes, it can be 30 hours. So how we can combine them together? That is a challenge. That is our research topic as well. To do that, this is, I would say, this is probably one of the most advanced modeling systems in the world called STEPS. This is not from us, but it's from our collaborator in Australian Meteorological Office. He developed this STEP system, nowcast, by decomposing the radar image into different scales and combine them together to take into account the movement of the echo or image or the radar signal, if you like, at different scale, and then combine them together. So you could ensemble forecast, nowcast. Once again, I cannot cover the detail. This is actually shows you how it is done in the UK. You can do this, you can generate a number of different realizations. For example, if you want to make forecasts for next 30 minutes, it can help you to create probably 30 members of ensemble, different realization. So this is one of the advanced sort of modeling system we have. And we didn't do that, but we make use of that modeling system. We see how it works with our hydrological forecast. And this paper published in a conference, and this is showing how that kind of steps can be coupled with this hydrological forecast. We generate ensemble hydrological forecast or flow forecast as well, which worked very, very well to my surprise. Initially, I thought, I don't quite trust that sort of model, but I found out it was actually quite good. So this is that sort of a new source of forecast called nowcast. The other side of our research, we try to address this sort of uncertainty. Of course, uncertainty is a big problem in this numerical weather prediction as well as the hydrological forecast. One of the things is because of this chaotic nature of the nonlinear system. You probably be familiar with this picture, like butterfly wing. If you think about it, the cloud of butterfly wing in Amazon can cause hurricane in the Gulf of Mexico. You probably have heard about that theory about chaotic. This really address the situation where the initial condition, this kind of uncertainty can cause big difference in your future forecast. There are also some other sort of uncertainty as well. This is another aspect of our research. We try to quantify the uncertainty in the model. And we look at the most recent advancement in this research area. We've been trying to sit in front of this kind of research line. This is what we're currently doing. We have a high resolution numerical weather prediction model now down to 1 kilometer resolution. For small area, we have a mobile community-oriented, very high resolution radar for urban flood warning application. For that matter, I'll be showing you in the next few slides another so-called project we've been doing. This is so-called small radar, flat panel radar. The X-band, I cannot tell you what the X-band means, but just keep in mind it's very small compared with that big radar. You can carry this radar on the so-called on the trailer in a small car even to drive your car anywhere to monitor weather. So it is quite advanced radar as well. And more recently, we just finished this project. So I had a project with some Chinese partners with, UK, these companies, the big name like Wallingford, and we have Nanjing University of Information Technology, and we collaborate with Guangzhou city government and to do this kind of early warning system using that advanced weather radar. This is the radar we use in Guangzhou, and this is the coverage, a small area with several radar. The big advantage of this radar is it can give you very, very extremely high resolution, a few hundred meters, it's so-called straight scale information, and it scans every 5 seconds. The scan is not mechanical scan, it's electronic scan. Every 5 seconds, you get image with a few hundred meter resolution. It's amazing. You see here, 60 meters and 90 seconds. And this is how they scan. This is traditional weather radar. You can mechanical scan, but for this other radar, it's just electronic scan, very quick. And this is study area. This is Guangzhou city, very big, I believe Hong Kong somewhere here. And then we have our study area, and we collaborate with HR Wallingford and use their model SEM live coupled with our radar and look at the urban drainage area to do the flood warning for the urban area for China big city. Area is quite small, 2 square kilometers. And we built a very detailed so-called drainage model across that region. Well, this showing some, I grabbed this picture, this slide from one of my collaborators written in Chinese. Apology for that, but just to give the idea, if you're from China, you can read it. This would happen in May in 2007. This what it looked like in that area, okay? So early warning apparently very important. So that is why we invested in that weather radar. We're doing the research to see how we can give the local people, residents, this kind of early warning as long as possible. And this is our initial analysis to use this new sort of radar. As you can see here, it detected this kind of quite strong rain band very well. There's a rain band here, very heavy rainfall with very short period of time. for another event, of course, 2019. This so-called quality control error analysis we have done. This will give you an idea. This actually is a nowcasting. It's a 30 minutes beforehand. This animation, and actually it worked very, very well. Then after that, we can run the forecast on flow, the urban drainage, to get an idea how large area would be inundated in that location. Right, that was one of the case study we did in Guangzhou, and which the result quite, I would say, encouraging. So we will carry on to the similar research in future as well, using this advanced weather radar coupled with numerical weather prediction, coupled with hydrological forecast. Really works very well. So that's a research line. Another research line in terms of computer modeling in my group is so-called artificial intelligence, machine learning. Basically, we're trying to use this kind of new technique to address climate change impact. As you can imagine, climate change impact study recently, I would say, mainly based upon the big data we have. You have climate projection, and then how we can generate. So these are the overall understanding from this huge amount of data. The existing study only look at, small areas, very, very small area, look at about, 70 years, for example, 50, 70 years, look in the future. But how we can generate so-called the overall scenario for a large area, for countries, for a continent, for the whole of the world. The big challenge is data amount. It's huge data. How you can summarize? So we rely on AI, so machine learning. Just to give you an idea, so this is one of the studies once my PhD student had been doing, looking at the UK, not the UK actually, it's Great Britain. Look at the past 100 years of data. So every day you have an image. So that image has a resolution of 1 square kilometer. So you can think about how large the data is. There's one image, 1 kilometer resolution every day, 365 days per year, 100 years. How we can generate this? So that overall description, how we can identify the climate change impact that depend on the big data analysis and machine learning. And also we extend our research to Australia, even bigger country, to see the pattern. This is something published recently using that sort of toolbox we developed. Look at something in future, so-called non-stationarity modeling of the kind of extreme rainfall event. Once again, based on base data, based on the Monte Carlo simulation, what you can see here, this is over the last 100 years. You can get an idea about the trend, and the uncertainties here as well. I would say this is something I think they stand in front of a research line, and we need to do something probably more in this area as well. So if you are interested in this area, please contact me if you want to know more. This is something really, really new, not only for us, but also for the whole community in the world, research community. This is something very, very interesting as well. This also we published this paper as well. Right, I think I finished my presentation. Hope you have learned something. This is, I would say this is not a normal teaching. Just to give an idea about the research I've been doing. For the normal teaching, I would say this is more or less the same. However, the level of the content, of course, will be different. This is how we normally interact with students. Nowadays, we have online teaching. I also have face-to-face teaching here at Swansea as well. So in case you have more questions, please do feel free to ask. I also have written down a few lines in Chinese as well for some Chinese applicants. If you want to know more this information about engineering, the study, how you what kind of course and how it's look like or feel like a life and study here in Swansea. Please do get in touch with me using my email address there. You can have a look at my webpage as well to find out something probably interesting to you. I also have a Twitter account. You can follow my Twitter account and see some recent updates. Thank you very much.